I will later read the CV or the biography from Prof. Tetsuya. Yeah. However, at the beginning, I believe it is better for us to start on time, even it is like 3 minutes or 5 minutes late. Sorry, Prof. Tetsuya, for that. Yeah, I'm gonna read your CV later after your presentation or before the Q&A.
Okay.
Yeah. Then the floor, not the floor. Okay, the audience is yours. The screen is yours. Okay, please, you may start now. Thank you.
Okay, thank you. I will share my screen. Can you see my screen now?
Yep.
Okay. 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 Today, I'd like to continue on chapter 3. Last time I couldn't complete the chapter 3, so I will talk about the chapter 3 a little bit. After that, I will go to chapter 4. Okay. Yeah. So last time I talked about the basics of transmission media. Today I'd like to a little bit talk about more. I already explained the fundamentals of the electromagnetic wave and the reflection, reflection, and so on. So today I'd like to talk about the one of the topics in Doppler effect. Doppler effect itself is well known, but I like to pick up some interesting feature, and I like to a little bit talk about the wave propagation in waveguide and some features in optical fiber transmission. I prepared the mathematical expression, but I don't want to focus on the mathematical expression. I like to focus on the physics inside. So please focus on the drawing or my explanation. It's not necessary to follow all the mathematical expression here. Okay, here I like to talk about the Doppler effect. Doppler effect is well known. The frequency observed by the moving object will be shifted from the original one. It's well known. So if we use the relativity, we can describe the Doppler effect by this equation. F is the original, the frequency, and C is the speed of the light, and the V is the speed of the moving object. By using this equation, we can describe the frequency shift. And I don't want to explain the detail of the mathematics, but finally, we can get a simple equation like this. The frequency shift can be described by simple equation, the moving speed V over the speed of light C. For example, the frequency shift due to Doppler effect for 3 GHz radio wave source moving with the 360 GHz, 360 kilometer per hour is 1 kilohertz. This is a typical situation in a high-speed train. If we observe the microwave from the high-speed train, the frequency shift would be 1 kilohertz. Okay, here I like to talk about the relationship between the Doppler effect and the phase delay. Here I like to talk about the phase delay. If we observe the electromagnetic wave here and here, of course, here is some phase difference due to wave propagation delay. Light wave coming from here, and it takes a particular the time duration caused by the wave propagation from point A to point B. So the wave at point A can be described by the simple equation. I don't want to get into the detail, but it's quite a simple one. Here is the frequency fluctuation term, and it shows the initial phase. So if we consider this one is a kind of a reference, we can just use this equation. It oscillating with frequency, and it has an initial phase. And if we look at the point B, of course, it would have phase delay due to propagation from point A to point B. So it can be described by this equation. Lambda is the wavelength. So the phase difference due to the wave propagation delay between the 2 points would be like this. It's well known. It's a very simple equation. It's not directly related to Doppler effect at this moment. Just I described the phase delay due to a wave propagation. Okay, here I like to explain the Doppler effect. Okay, here I like to consider now moving object moving from point B to point A. So if we observe the electromagnetic wave from the moving object, the frequency will be shifted due to Doppler effect, as I mentioned. And at the point B, of course, we have phase delay due to propagation. So the phase difference between the wave observed at point A and on the moving object can be described by this equation. And distance between A and B should be described by the Lorentzian Lorentz the transform. I mean Lorentz contraction. But if the speed is small enough, just we can approximate this one by L. So we can just use just a distance L. So the duration of the movement between point A and point B is approximated by this one. Just we can divide the distance by the speed of the moving object. So when the moving object arrives at the point A, the phase difference can be described by this equation. Just I put this one into this equation, T. So the phase difference is equal to 0. So just I explained two things. The phase difference between these 2 points due to phase delay due to the propagation of the wave. And another one is the Doppler effect on the moving object. So if we monitor the wave here and here, of course, we can see the phase difference. And if we measure the waveform by the on the moving vehicle, we can observe the frequency shift. And finally, we can get this equation. Okay, here is some explanation. The phase difference due to the propagation delay, 2 pi L over lambda, is compensated by the phase shift due to Doppler effect. So if there is no Doppler effect, we may have some phase gap on from the point of view of the observer on the car or sitting here. So thanks to the Doppler effect, we can ensure the phase continuity, even if you are riding the car or sitting at the particular place. So I like to repeat the explanation. The phase observed at the moving object is equal to the phase measured by a stationary observer at the point A, when the moving object arrives at point A. On the other hand, the phase of the EM is equal to that of the EB when the moving object at the point B. So if that guy is here, the phase continuity is ensured, and the car can come to another place, but even in the another place, the phase continuity is ensured. I think, I'm not sure you're interested in this one, but I didn't find such explanation in the other textbook, so I put this explanation in my book. As my point of view, it's quite interesting, and the Doppler effect ensure the phase continuity in the various conditions. Okay, this is just another topics. Okay, here I'd like to move on to another one, the electromagnetic wave propagation in the waveguide. I don't want to go into the detail of the mathematics. I'd like to explain just the basic, the idea. We can use various types of structure, rectangular, cylindrical, and so on. And we can use various types of material, metal directly, and glass. And it can be single mode or multi-mode. The characteristics depends on the shape and the size of the waveguide, and of course the material. And in the last week, the lecture, I talked about the reflection and refraction. Wave propagation in the waveguide can be described by the combination of the reflection and reflection. And the volume between the surface acts as the core of the waveguide. The major part of the electric wave power would be confined in the core, but some is radiated through the planes. It would cause the loss in the propagation. And the parallel rays here would form the waveform inside and outside of the core. When the ray propagates inside the core effectively and interfere constructively, and we can confine the electromagnetic power in the core. The ray out of the core interfere destructively with each other, and such interference conditions are satisfied with a particular ray angle on a fixed frequency. The propagating wave with a ray angle that satisfies the interference condition is called mode. If the angle is different from the particular condition, in that case, we may have the strong electromagnetic wave outside the core. In that case, we cannot have the effective propagation in the waveguide. And we can define the speed of the electromagnetic wave in the waveguide. The waveguide propagates like this if we describe the electromagnetic wave by the ray, as you can see here. So the wavefront will be like this. In that case, the phase velocity, as I mentioned in the lecture, can be described by this equation. Of course, the cosine theta would be smaller than 1. That means the phase velocity would be faster than the velocity in the vacuum. But as you know, the information and the energy can be transferred by the group velocity along this direction. It can be described by this equation. It will be smaller than the speed of light. So if we just look at the phase, we will miss something. So we should use the group velocity if we want to discuss the speed of the signal. Okay, here I'd like to move on to the last part of this chapter, optical fiber transmission. I will talk about 3 items: optical loss and chromatic dispersion and nonlinear effect. This shows the typical optical loss in the optical fiber. The horizontal axis shows the wavelength of the light, and the vertical axis shows the propagation loss, dB per kilometer. It shows the minimum propagation loss around 1.55 micrometer. That's why we often use this wavelength for long-haul transmission. The loss will be 0.2 in a standard single mode fiber. If the wavelength is longer than this, the loss will be larger due to infrared absorption. If the wavelength is shorter than this, we may have the Rayleigh scattering. Rayleigh scattering caused by random structure inside the glass. And the loss is small enough for optical fiber communication. But if we want to make a long-haul transmission system like the submarine cable, we have to have the optical amplifier. We can use the L-beam doped optical fiber to amplify the optical signal. We put the optical pump and to excite the state of the L-beam. And L-beam can induce the stimulus, the emission. Maybe you learn somewhere by using the stimulus and the emission, we can get amplified optical signal. This is the basics of the optical loss and the amplification. And in the here, I like to a little bit talk about the signal modulation. The modulated signal contains more than one spectral component. As you can see, the group velocity is defined for the envelope formed by the spectral components. We can consider one of the simplest modulated signal. It has only two spectral components. There are two spectral components, and omega describes the average, the angular frequency. So the high frequency component has some deviation from the average. Here is the lower frequency component, and the wave number k would be a function of the frequency. So we can describe like this. Here we can describe the two frequency component, the spectral component, like this, this one and this one. It's not so complicated. As I mentioned, the wave number k can be described as a function of the angular frequency. If the delta omega is small enough, we can use a Taylor expansion. We can use a Taylor expansion for this. Just by using the Taylor expansion, we can get the simple equation like this. By using the transformation formula for the triangle, the function, as you know. So it has a two component. This component describes the time domain profile of envelope. This component shows the high frequency oscillating component with the omega t, and this one shows the envelope oscillating with the low frequency delta omega. So here we can define the equiphase point of the envelope. That means it should be stationary. If we can define this one, we can focus on some particular point on an envelope, for example, here. And by differentiating this equation, we can get a simple equation. Okay. This part should be just 0. And this part should be just a delta omega. And this part should be del dt, dz over dt. So we can get this simple equation. And this show the group velocity. So some particular point in where envelope propagate with the speed. And the wave number is described as a function of omega. So we get the mathematical expression for the group velocity. I will skip the detail, but anyway, we can describe the Vg by the refractive index. So finally, we can get a group refractive index. Someone is talking. Okay. Okay, I skipped the detail, but anyway, we can define the group refractive index. Just by using this, we can define the speed of the signal. Okay, and by using the group delay, we can define the time duration for the signal propagation over some unit length of fiber, just by using simple equation. And then finally, we can take the we can get the deviation of this one. Deviation of this one again. I will skip the detailed explanation, but I like to focus on just this part. By differentiating the delay, we can define the chromatic dispersion. If the speed of a group speed has some group delay, has some difference according to the wavelength, the waveform would be deformed. I skip this one. Okay, I try to explain what's happened by using this slide. If we generate some signal, the signal would have some pulse shape like this. And pulse shape, if we look at the pulse in the time domain, it will be like this. And if we look at the signal in a wavelength domain, it has some spectral component. And each spectral component has different group delay. That's why we try to get the difference of the group delay. And if we just look at the wavelength component, the spectrum shape is same, even if we have some delay difference. But if we look at the time domain profile, the shape would be degraded because each component arrives in a different time. This is the effect of dispersion. So if we have the dispersion in optical fiber, it limits the transmission speed. Okay, here is some simple example. In the standard single mode fiber, the typical dispersion would be 70 picosecond per kilometer per nanometer. That means if the wavelength difference is 1 nanometer, the signal would have 17 picosecond delay difference for 1 kilometer transmission. If the transmission distance is 10 kilometers, in that case, the delay would be 170 picoseconds. If the bandwidth is 2 nanometer, in that case, the delay difference would be 34 So just by using this, we can evaluate expected the time the difference at the receiver side. I skipped the detailed mathematical expression, but for 10 gigabit per second of keying modulation, the transmission distance limit given by 70 kilometer. If the transmission distance is over 70 kilometer, the wave would be the wave shape will be completely deformed. But for 100G, the limit is less than 1 kilometer. This is a very important point. I skipped the detail of the explanation, but you can see the basic function. The B describes the bandwidth. If the bandwidth will be double, the limit will be the 4 times smaller. This is a very important point. But now we can use the dispersion compensating fiber. It has the negative dispersion. Or we can use the digital signal processing to compensate the dispersion effect. Dispersion effect is basically the linear effect. So just by using the linear matrix, we can compensate the dispersion effect. Okay, this is the last one, nonlinear effect. It's not easy to describe the nonlinear effects by the simple mathematics. So I don't use any mathematics here. There are many types of nonlinear effect. Here, I like to focus on a simple one. The simple one is like this. Reflective index depends on the intensity of the optical signal. So here and here, the reflective index would have some difference. And if we have some multi-channel scheme, if we put them very many optical signal in an optical fiber, we may have some correlation between optical signals. And the famous one is here, stimulated beryllium scattering and Raman scattering. The stimulated beryllium scattering caused by acoustic phonon in a fiber. The fiber would have some small vibration due to the acoustic wave. It generates backward propagating wave. The Raman scattering is caused by optical phonon. The mechanical vibration with the high-speed component. This effect can be used for optical amplification, but it would cause undesired nonlinear effect as well. And nonlinear effect compensation is very difficult. Here is some example to show the difficulty, importance of the nonlinear effect, the compensation. We can put many optical signal in an optical fiber. If all the transmitter and the receiver placed in the same place, we can gather all the information. And maybe the required computational power would be large, but anyway, we can solve we can compensate nonlinear effect. But in an optical network, we may have the complicated optical network like this. Here's an optical transmitter and combined together and distributed to the other different places. In that case, to compensate the nonlinearity here, we have to know the information of the signal of here and here. But if we want to share the information at the receiver side, we have to have another optical fiber here. And another optical fiber also causes the optical nonlinearity. So if we want to make such the all optical network, we cannot compensate the nonlinearity in principle. It limits the performance of the optical network. Okay, this is the end of the chapter 3. Okay, someone has some question. If you don't have, I'd like to move on to the next chapter. Anyone has some question on this chapter?
Any question maybe from audience? They can write down in the chat box, or you wanna continue to the what you call this seamless access system? Okay, please.
Okay.
I mean, yeah, the question might be at the end of your presentation, or another 20 minutes, I believe, for 15 minutes. Okay, yeah, please, Prof. Yeah.
Okay, I'm going to I'm moving to the next chapter. Okay. I have to stop the sharing first. Now you can see my slide.
Yes.
Okay. This one, chapter 4, the concept of seamless access system. Okay. Yeah. Oh, sorry. It works funny. Okay. This chapter has a 4 parts. In the first section, I'd like to talk about the needs for seamless access network and the configuration of the seamless networks, and the power consumption of the short distance radio link, and the carrier frequency and the spectral efficiency. It shows the importance of the new radio technologies to mitigate the spectrum congestion. Okay, this shows the needs for the seamless access network. It shows the basic configuration of the mobile network. In the mobile network, we have to have so many the base stations, antenna, remote antenna.
Prof. Tetsuya, excuse us. We cannot see your screen. Yeah. I mean, have you shared your screen yet?
Okay, maybe.
You will not share anything? Sorry.
Okay. I had some error message from Zoom.
Do you need, I don't know whether we can help from here. Have you sent your PowerPoint file to us?
Okay, yeah, I restart my Zoom app, so just wait for a while.
Okay, no problem. You restart your computer. That's why we need sometimes. I believe we can maybe whether the question already there, or how many minutes you need? I mean, for the slides. Prof. Is gone. Question from audience, please. I'm waiting in the chat box.
Yes, one question going up.
Yeah, we're still waiting. We are waiting for the speaker. Prof. Tetsuya, I believe he's disconnect, right? He's disconnect, and my computer is not there. Yeah, he's not there.
Yes, he's coming.
Alex, I will read the.
He's coming.
Alex, I will read your question later. Prof. Tetsuya, are you there? Are you there, Prof. Tetsuya?
Now can you hear me?
Sorry.
Okay.
Yeah,
okay.
now it's okay. I'm sorry. I just read your message.
Yeah. And,
Yeah.
and can you see my slide?
Clearly. Okay, thank you.
Okay.
Yeah, you
Okay.
can start.
Okay. I change it to now. Now you can see, I hope you can see in presentation mode. Okay. Okay, I'd like to go to the conceptual slide. We have to connect the many baseband unit and the remote antenna unit by the optical networks. There are a couple of functions at the baseband unit. It can be categorized into two parts. We call it, the first one is called baseband unit, BBU, which convert the baseband signal, digital signal, into a radio waveform. And another one is the antenna unit. Antenna unit emit and receive the radio wave in the air, as you know. So we have to divide the function into two. The box describe the BBU. This one is a remote antenna unit. And BBU are connected to core networks through mobile backhaul links. Mobile backhaul links that transfer digital data stream in the same way as a conventional digital optical fiber communication system. So the baseband unit can exchange the digital data with the other baseband unit or with the some server in a backbone network. On the other hand, mobile front haul, MFH, connects baseband unit and the remote antenna unit. And the purpose of mobile front haul link is to transfer waveforms for radio services. So in that part, we have to transfer waveform. In the blue lines, we can transfer digital signal. The waveform transfer can be offered by analog or digital radio over fiber. There are two types of the transmission scheme. And now the digital radio over fiber are commonly used. There is the international standard called the CPLI, Common Public Radio Interface. The mobile front haul system are defined by the common the CPLI. For 3G and 4G systems, the required bit rate is smaller than 10 gigabit per second, so we can use the low cost, the 10G, the system. But for 5G, the required bit rate is larger than 100 gigabit per second. So it's not easy to use the digital radio over fiber or 5G directly. To overcome this difficulty, the function split options are proposed, where some of the functions in the baseband unit are moved to the remote unit. but so the required bandwidth for the mobile phone tower will be smaller than in the display. But the configuration of the remote unit will be complicated because some functions should be moved from BBU to remote antenna unit. And here I'd like to a little bit talk about the advanced configuration. We can use a fixed wireless link in a part of the mobile network. Of course, the transmission capacity will be should be large enough, because if we use the conventional radio system here, the transmission speed will be much smaller than in the optical fiber, so it will be in a bottleneck of the total system. The terahertz or millimeter wave fixed wireless system are feasible for high-speed links. We can use a high-end antenna to enhance the transmission distance. In a traditional microwave band, we have to take care of the various types of radio services, and the bandwidth will be very small. But in a terahertz band, we can use a wide band. Okay, here I'd like to explain the configuration of seamless networks. As I mentioned, we can use a radio over fiber. It shows the base configuration of radio over fiber. Here is a radio wave signal which we want to transmit, and we can modulate the optical intensity by the waveform in the simplest case. And we can take out the waveform just by using the OE conversion. OE conversion means the optical to electric signal conversion. If we use such a simple analog radio over fiber, this configuration will be simple and latency is very small because there is no complicated digital signal processing. And by using optical fiber, the transmission loss will be much smaller than any coaxial cable, metal cable. Okay, here's an example of the bridge which connects the radio transmission part and the optical transmission part. As I mentioned, we have to have so many radio link and the optical link. So we have to make a combination of the optical fiber link and the terahertz link. So we should have many interfaces, as you can see here. Here is the baseband signal, and the baseband signal is converted into an optical signal. And at the interface, we should have the optical receiver and the radio transmitter. And radio signal should be converted into a baseband signal, and we should have the optical transmitter. So setup will be very complicated. There are so many conversions. And in optical the transmission technology now, we can use complex digital signal processing to increase the total capacity. In that case, we have to have the DSP for optical signal generation, optical signal detection. And in radio part, we also should have the digital signal processing for radio waveform process. And here is a DSP for radio signal detection and DSP for optical signal generation. So there are so many DSPs if we use the signal processing scheme. But if we can use the radio over fiber, we can skip some DSPs. If we can have the comprehensive signal processing for radio part and the optical part, we can skip some of the digital signal processing. This is the basic concept of radio over fiber for seamless access network. And in some application, we have to send some local oscillator signal for frequency conversion. We should transfer the waveform in a lower frequency signal. For example, if we focus on the terahertz application, if we use such a simple configuration, the required bandwidth for the OE conversion would be very high, the 300G or something. It would be costly and not so effective. So in that case, we have to send the waveform in the intermediate frequency component, that means the low frequency component, and we can convert the frequency at the antenna side. To achieve the optical frequency conversion, we have to have the local oscillator signal. And local oscillator signal also transferred over the fiber. Okay. How much time do I have? Okay, I check my.
10 to 15.
10 minutes. Okay.
Yeah.
Okay, so I like to move on to the another point. The here I like to talk about the power consumption of the short distance radio link. The transmission capacity can be described by the SNR, maybe you know, by using the Shannon-Hartley theorem. Okay, just this one. Okay, I can finish in 10 minutes. In the next the lecture, I will explain the more detail about the Shannon-Hartley theorem. But here, I'd like to just remind you the basic equation. The total transmission capacity can be described by the bandwidth B and the SNR. If the SNR is large enough, in that case, we can describe the capacity just by this simple equation, and the noise can be described by the thermal noise, the bandwidth, and the temperature. So if we use such a simple equation, the maximum transmission can be given by such an equation. I will skip the detailed explanation, but if we can keep the SNR constant, if the SNR is constant, the signal power S must be proportional to B, of course. So in that case, the maximum capacity can be given by this equation. If the power consumption of radio radiation is proportional to the signal power, the total power consumption can be described by this equation. So this is the signal power, and the power consumption would be proportional to the signal power. And we have to add something, constant power, for some computation or user interface or something. So by combining these two equations, we can calculate the power consumption per bit. And I will skip the detailed explanation, but the power consumption per bit can be described by these two components. This one will be the constant, and this one will be inversely proportional to the bandwidth. And by using the sum formula, we can get the simple equation. And the minimum power consumption per bit can be described by this simple equation. Here is the logarithm of the 2 and the noise part. If you're interested in, you can refer my book later. And but so if we if the equation is if we can use such equation, the power consumption per bit would be independent from the modulation scheme or something like that. It should be constant. But here is some of the data, the bit rate and the power consumption. If the bit rate is higher, the power consumption per bit will be getting smaller. I think it's very interesting. If we look at the power consumption of the car or motorbike, if we want to purchase the high-speed car or high-speed motorbike, I think the gas consumption would be larger than in the economic, the compact car. But if we look at the power consumption of the ICT, radio communication system. First, the radio system offer low power consumption. It's quite interesting, I think. If we use a millimeter wave transmission system, power consumption per bit would be much smaller than the the Zigbee or Bluetooth. This is because in an ICT system, this part would be very large, constant power. It's not the proportional to the radio power. If the major part is proportional to the radio power, it should be constant like this. But in ICT system, the constant power unit would be dominant. So if we can use the high-speed system, we can reduce the total time duration, and we can reduce the power consumption in power management or computer, the GUI part or something like that. And at this moment, we cannot have the data of power consumption in a terahertz system, but we can expect something. In a terahertz system, we can expect high-speed transmission close to 100 gigabits per second. If we can, if the power consumption would be on the line of the trend, the power consumption would be comparable to the optical fiber link. So the terahertz communication would offer very low power consumption. This is just the rough evaluation, so we should discuss in detail to predict the power consumption precisely. Okay, I'd like to move on to the last one. As I mentioned, in a conventional radio band, I mean the microwave band, the mitigation of spectrum congestion will be an issue. There are so many radio services. To solve this issue, we have to take two options. The first one is to increase the spectral efficiency by using a modulation format or MIMO or beamforming. Another one is to explore new radio frequency resources. That means the high frequency band, millimeter wave or terahertz. So to describe the contribution to the congestion mitigation, we defined a very simple index, CFSC, carrier frequency spectral efficiency product. Just by taking the product of calculating the product of the carrier frequency and the spectral efficiency, we can show the contribution to the spectral, the congestion mitigation. Okay, this shows the CFSC as a function of the carrier frequency. Each spot describes the terahertz research result. If the frequency is higher than 300 gigahertz, CFSC will be getting smaller because we have to, when we increase the carrier frequency higher than 300 gigahertz, we have to sacrifice the spectral efficiency. But below 300 gigahertz, we can increase the carrier frequency without losing the spectral efficiency. So the contribution to the mitigation would be in a maximum at the 300 gigahertz. Okay, so if you're interested into advanced the device technology, I think you can focus on the frequency above 300 gigahertz because due to the lack of the advanced device, we have to sacrifice the spectral efficiency. If you're interested in the implementation of the system, we can focus on the frequency band below 300 gigahertz. So CFSC would be useful to describe the research trend. Okay, that's it from me. Thank you very much for your attention. Okay, I have a question. Okay, the question is on seamless network. Seamless access network can exist or destroyed by another system. Okay, I think in the beyond 5G or 6G, we have to offer the comprehensive and the high performance network service in the, of course, in the city center and the mountain area, remote area, and so on. So we have to combine various types of transmission media. This is a very important point. We have to use the conventional radio band and the optical fiber, millimeter wave technology, terahertz. That means we have to have so many interfaces bridging the different types of the transmission media. This is the new concept. Actually, in the existing mobile system already have such a function, but in a future system, we have to focus on such aspects. So the seamless access network itself is not a so new concept. Even in our system, it has such aspect. But in a future system, we have to focus on such aspects. So there is no clear difference between the existing network and the seamless network. Just I want to focus on the importance of the interface between the different the transmission media. So I think seamless access network can exist or destroyed is my answer for this is not so clear, but the seamless access network showed some direction of the evolution of our system. So we can use the conventional technology and we can add some new the aspects. Okay, any other question? Okay.
So sorry for the disconnected.
Yeah.
Previously, we got blackout here. I show 3 questions already here. Have you answered one question?
Yeah. I got some other question, and the second question is.
I mean, have you answered the first question? The first question was the limit of the frequency for the fiber optic or light. It was answered or it wasn't? Have you answered that question?
Okay. Yes. The optical fiber itself does not have the limit in the sense of the waveform transfer, but we have to have the optical modulator and demodulator. Maybe normally we will use the photo detector. Such device has some limit in the bandwidth. Even if we use an advanced device, it's up to 150 gigahertz or something. That's why I think I explained we have to use an intermediate frequency solution. In the intermediate frequency solution, we can transfer waveform in a different frequency. And at the antenna side, we can transform we can change the frequency. This is the one solution. So the limit is the frequency is limited by the optical devices. Okay, the last one is unstable networks. Okay, this is a very important question, and of course we have to consider various types of aspects. Actually, in our group, we are working on the instability of the fixed wireless system. If we use a high frequency system, even if we have the small mechanical vibration of antenna, it will cause some signal deformation. So we have to take into account such effect. Maybe you know the rain attenuation is well known. In addition to this, we have to consider about the mechanical vibration by the wind. Normally, if we have the strong rain, in that case, we may have the strong wind as well. So we have to take into account these two aspects to ensure to increase the stability. And as I mentioned, in a future system, we have to use various types of transmission media. By combining the various types of transmission media, we can increase the stability. For example, if we use the optical fiber and the terahertz system and the optical wave in the air, the characteristics has difference. In a foggy condition, the optical wave in the air is not so useful. It will be disconnected, but the terahertz is okay. But if we have heavy rain, in that case, we can use another solution. This is one of the example, but it's not easy.
Yeah, the other question, due to this breakout, I told you, I thought I missed it. Your opinion regarding the seamless network, whether it will be, stand out in the future or it might destroyed by the other systems. What do you think? Have you answered the question? I was, missed it.
I already answered the question. Yeah,
Okay.
yeah.
Okay,
We can use the
very
existing
nice.
technology and we can add some more. And I got the last one. What is the highest frequency that can be reached? I showed carrier frequency spectral efficiency product in the last part of my presentation. It showed 300G would be the typical target at this moment. But of course, if we can use advanced device, we can increase the frequency more. But this is just my opinion. The upper limit would be 1 terahertz, because if we go farther, if we want to go farther, the attenuation in the air will be very, very high. So it's not easy to increase the frequency more higher than 1 terahertz if we look at the radio technology. In addition to this, we have to take care about the mechanical stability. As I mentioned, if we use the millimeter wave technology, we have to take care about the mechanical vibration of antenna. But if the wavelength is much shorter than this, maybe it's not easy to make a stabilized vibration. This is my opinion. But if we can find, if we can get some more new device, maybe it will be solved. But at this moment, the 300G is a feasible target in a terahertz application. And for implementation, it should be around 100G. And the upper limit in research will be 1 terahertz. This is my opinion.
Yeah, okay. Well, while waiting for the last question, if there is one from the audience, I show in the chat box there is a from Google. I believe it's the attendance list. Please sign into the attendance list for the audience. Sign into that, and then I believe I promise all of you to introduce Professor Tetsuya in the Q&A session. I'm gonna read a short CV of yours. Yeah, Prof. Tetsuya Kawanishi. He is now working in Waseda University, Faculty of Science and Engineering, in the Electronics and Physical Systems Department. The bachelor and master and also the doctor engineering degree you got from Kyoto University, yeah, Prof. Tetsuya?
Yes.
I show a lot of experience of your work here. I'm just gonna read the now I'm not gonna skip it. You were the visiting scholar in University of California at San Diego until 2004, from 1 year there, and you are also director from Lightwave Device Laboratory at previous years, and until now you are a professor in Waseda University. You are also the IEEE fellows. Yeah, I believe
Yeah.
until now, right? Not only for the Electronic Device Society, but also Microwave Theory and Techniques Society and many society. I'm curious about this. I'm curious about this IEEE Photonic Society. You were not there anymore until 2019. However, you were active in the others.
Yeah. My duty
Mhm.
is already completed.
I see.
Yeah. I worked
However, it
as
is. Yeah.
I worked as a board of governor for 3 years. Yeah.
Yeah. Yeah. Okay. Yeah, it is our really, I mean, great opportunity to have you here. Yeah, to listen to your lecture. I believe we still have another series. I don't know until 5 or 4. Today should be the fourth one. Yeah, the fourth
Yes.
series of your lectures.
Mm.
You still got 5 or 6. I was just want to inform the audience.
The fifth one will be held in next week.
Next week or this Thursday. Next week. Okay.
Yeah. Next
If it is
week,
next
Monday
week Monday.
morning. Monday morning.
Monday morning. Okay.
25th.
Yeah. Yeah, the fifth, and then it's gonna be the last one, or you have another 6?
I will have that in total 10. So
10. Okay, yeah.
yeah.
Sorry, I was just okay. Good, very nice.
Yeah.
We for the actually here I was introduce you to the audience since many first year students are here. From my class, I taught them to follow your lecture today because it is also an opportunity for them to practice their listening in English, and also I believe some of them also learn the physics of electromagnetics and electricity. So I saw in the previous series, the third one, it is like the Doppler effect. We get this also in our course, so it is really interesting for the first year students. I saw there is no more question here, and also the time is up. Even though I'm gonna ask one thing regarding the Doppler effect. You mentioned about the phase, frequency and phase. Yeah. How we distinguish the phase actually? I mean, by listening to the Doppler effect.
Actually, this is based on the interesting chat with my professor many years ago. So when I wrote my book, I remember the chat with my professor, and I initiated a discussion with my professor again. I summarize this one. I show you now the example. This is not the example from the electromagnetic wave, but the acoustic wave. So let's consider about the marching in the ground in the school. The kids are walking.
Marching band. Marching band.
Marching. Yeah, and the sound is from one side, and people are walking in the ground. If the kids are close to the source of the sound, their marching step is faster than the other side, due to the delay of the acoustic wave. But the kids cannot aware the frequency shift, but they can keep walking. But if we look at the situation from the other point, the step rhythm has some difference, this side and this side. But kids walking continuously from here and here, and here is the acoustic wave source. So they cannot distinguish this small frequency fluctuation, but thanks to the very small Doppler shift, they can keep walking. But if we look at the marching, the rhythm, here there's some difference due to the propagation theory. I had such the chatting with my professor about 30 years ago, and I remember that chatting, And I had a chance to have a dinner with my professor, and I initiated such a discussion, and he remembered that discussion. And I never found such a discussion in the other textbook. That's why I included these topics.
Yeah, it was really, grateful to hear that. Impressing. 30 years and you still remember that, discussion.
Yeah.
Okay.
Yeah.
Okay.
So
Yeah.
as a professor, I think I have to remember my chatting with my students. Maybe students will ask me 20 years later.
Yeah, okay. I'll take that as the suggestion for us as a lecturer to remember our discussion also with our students, right?
Yeah.
Thank you. It was really interesting, your speech
Yeah.
and also discussion. Thank you for the audience. Don't forget to fulfill the attendance list. And then for Prof. Tetsuya, we're going to see you again next week. And also for the other 5 series until the WCP completed for the program. The WCP, right. The visiting, word, professor, something, the program. WCP, right? I forgot the abbreviation. Okay, I'm sorry. Yeah, thank you, Prof. Tetsuya, and thank you, the audience, and also thank you for the co-host. I'm gonna close this, with the goodbye for Prof. Tetsuya, and then also Alhamdulillah, thank God, we are safe and sound until now. And Assalamualaikum warahmatullahi wabarakatuh. Good afternoon for the Professor Tetsuya. Afternoon here. And then I believe you're in UK. You are now in UK. Yeah, see you next week. Yeah. Okay, bye-bye.